You should be good.
I mean, yeah, I have a lot of.
Hello, good morning. Okay. Homework 7 and 8. Not 1 week later, but the 1 week later, the lecture is, oh, so.
Oh, it's working now. It wasn't in the turn for some reason.
Okay. Let's see. So this Tuesday following November 1 is a holiday for election day. And so we have day. That's the same day as you have the midterm exam 3. And even though you have more time for homework 8, I have nevertheless given extra time for that, even though your due date shows up as the same time as the exam. You can take some liberties and give priority to the exam over the homework, but be responsible about it. Your responsibility to complete it on time. I don't tell you exactly how much buffer I've given you so that you try to meet the deadline, but exactly that is about 24 hours. Time. That's for it. Any general comments or questions you want to address here for everyone that's useful for everyone? We have been talking about magnetic field for the last couple of weeks. There is a lot of analogy between electric field and magnetic field, but nevertheless significant differences. Also, one of the primary differences is that the source of an electric field is just a charge. If you have a positive or negative charge, it creates an electric field. But for a magnetic field, you need a moving charge. Unless it is moving, it will not create any magnetic field. That should raise a new question, which I will not be addressing in this course, which you will see it about in the next semester or so, if you were to study a little bit more physics. And that idea is really puzzling, and that is what eventually led to the idea of what is called special relativity. It is what Einstein popular for Einstein is a popular figure. His idea started from the way that if you have a moving charge, it creates a magnetic field. That means to say that if you were moving with it, like when you are moving at the same rate as a car is moving, the car looks like as if it is at rest. So which means to say that if you have a moving charge, it creates a magnetic field from what I have told you now. But if you were to move with it at the same speed, it is at rest with respect to you, which seems to suggest that with respect to you, the magnetic field should be zero. So magnetic field is a reference dependent quantity. And then you ask yourself, what does that mean? What does or magnetic field itself mean? What it will turn out is that magnetic field is different for different people. Exactly like velocity measure of a car depends on your speed. That is your reference. And in that sense, magnetic field can be completely switched off in a frame in which the charge is at rest, or for that matter, you sit on the charge. Like you go and sit on the charge, you're at rest because you're right there on it, and there will be no magnetic field. And then you would ask, what about energy associated with the magnetic field and so on? All that is converted into electric field. So that's just for information, and that is all I will be able to tell that in that context. Here, what we are saying is that we're not moving related to each other. Observer is always at rest, and the charge is moving with a velocity v with respect to the observer. So in that context, we have said moving charge. So is charge itself times its velocity v. So that's the source. It means to say that if v is zero, and it's no source of magnetic field. This is directly associated with a current carrying wire. If you have one charge moving, have a lot of charges moving, that's a flow of charges, and that's exactly a current in a wire. A controlled flow is exactly what a current carrying wire is. And for that, we say this is I, current in the wire, times dl. If you have a small piece of wire, then usually you don't associate a direction with it. That direction for the length of the wire is got by the direction of the current itself. If you have, this is your wire, the current in the wire, the length associated with it is just the length, but the direction for that length is coming from the direction of the current, even though we write the vector on top of dl. That actually is coming from the direction of the flow of the current. So moving charge creates a magnetic field, and due to the same reason, a current carrying wire, which consists of a lot of charges moving in coherently, if you want, that the flow of charges, that also creates a magnetic field. We talk primarily of two configurations. There are many in general, any configuration you can calculate. They're tedious, often you don't have mathematical functions describing the magnetic field. But the simple scenario we are talking about is a finite wire. If you have a finite stretch of wire carrying a current I, and if this is your observation point, which we call that T. T is observation point. And you can ask, what is the magnetic field at the point B? It depends on the length of the wire and the current I. Let's not I over how far you're from this wire. So this distance comes like a crucial rho. That's rho. Let's say that's the Greek letter rho. That's rho. Not how typically write it. Or let's say as a mu naught over 4 pi, or which shows up it's like 1 over 4 pi epsilon naught, and you can write this as 2 times I over rho. 2 times will be equal to infinitely long, and we have sine theta 1 plus sine theta 2. Where we would like to know what is sine theta 1 and sine theta 2. That's basically giving you the length of the wire. As if this was L1 and that was L2, that's a way of describing how much is the total length of the wire. It gives you the point, observation point where it is. And this sine theta 1 and sine theta 2 is basically a representation of those lengths. This is angle theta 1 and that's angle theta 2. The way it is written, I have written a positive sign in between. It is crucial whether it is positive or negative. Sometimes in your equation sheet it will be positive, sometimes it is negative. Make sure what is given in there. And that depends on the stripe. The arrows represent that in that arrow, in the direction of that arrow, the angles are measured to be positive. So here both the angles are measured in opposite directions to be positive. That's an unusual choice, but that's how it is written. What the direction of the magnetic field? The direction of the magnetic field is hold the wire and the curl of his fingers, this tip of your finger can have an arrow associated with it, and the curl of the finger gives you the magnetic field. Hold any wire you want, any current carrying wire, that tiny stretch of wire, when you hold it, creates a magnetic field at the observation point. So all of them will create the same amount of magnetic field here, be careful that we get farther. But in this case, all the directions are the same, so it is going in. But then if you are here, it is coming out, right? If you look at this as a curve on the board, everywhere on the right it is going in, everywhere on the left of the wire it is coming out, and it is actually circular. So if I were to draw that in here, so that's your magnetic field. It becomes a clutter when I draw the magnetic fields. So but that's how the magnetic fields will look like. And since they are circular, they are tangent to those circles. You say that's a symbol. That's a direction which in words means that they're circular around the line carrying the part. So you have a current carrying wire, let that be the axis of a cylinder. You have a circular nature to the cylinder, and the direction of your right hand rule gives you the direction of the magnetic field. That's one configuration, that's a straight line, which will be necessary to build or more complicated configuration. And another is a circular wire. And we say it is a circular R, if it was part of a circle, and that's a current carrying wire. A total circle will just be a complete arc, if that was making an angle of 2 pi, that will be a complete circle. And the magnetic field, in this case, the special case is that we talk about only at the center. So the observation point here is the center. One could ask, what is the magnetic field anywhere else? Yes, we can calculate it, but as I said earlier, it is involving more complicated functions. They are called elliptic integrals, which you haven't studied it yet. Elliptic integrals are pretty much functions like trigonometric functions. What you do is that if you ask yourself, what are sine theta and cosine theta? These are functions which are just symbolic representations of some complicated form, or usually you say it's a series. But what is the role of that? It comes again and again. You use a vocabulary to mean that sine theta means this series. More than that, if you have to add two sine functions, sine of theta 1 plus sine of theta 2, you find or you discover that, oh, I don't have to do this in this manner, it has this following pattern. So simple functions like trigonometric functions have a lot of identities associated with it. We have been working with it for the last 2000 years, or probably 3000 years, and we have a lot of identities associated with trigonometric functions. When it comes to other functions like elliptic integrals, we do know a lot of identities, but not as many as we have for trigonometric functions. So elliptic integrals are harder to work with because not many people have worked with it. Only in the last 400 years we have been working in it. Electric integrals came into existence only in the last 400 years. Trigonometric functions are about 3,000 years old. So that's the difference between the. Sometimes you get stuck with identities and it's not there already, so you got to really discover them again. So that's the difference. So in this course, we will not deal with observation point anywhere outside. Due to that reason that we don't have the idea of electric integrals yet. I should say that the magnetic field on the axis of a circular wire is simple. They can be written in terms of rational functions. Rational functions means some functions like this, where it is algebraic. Some polynomials in the denominator, some polynomials in the numerator, and those are simple functions to deal with. And they can be the magnetic field on the axis of a circular wire can be written in terms of rational functions, and I expect you guys to know that, but I'm not covering that here. On the center, it is significantly simple. It is again, if I were to hold the wire with the right hand rule, it is coming out of the board. So you will see hat, say out of the board. Times mu naught over 4 pi, it always sits there. Just a spectator, depends on what units you're using, and it is 2 pi. Actually, I can say 2 pi. I was thinking of it as full circle, so it's I over rho times just the angle theta. Whenever angle theta shows up separately, one should worry about in what units do you represent that. Whenever angle theta is coming separately, not inside a function, it is necessary that you say it in radians. Inside a function, like trigonometric function, sine of theta, you have the liberty to use it in terms of radians or in angles like degrees and so on, and your calculator can accommodate for that. But if it is coming separately, you don't have that choice, so it is understood that this is always in radians. So this is in radians. Which means to say that if it is a complete circle, this becomes an angle 2 pi. Theta is 2 pi means it's a complete circle. Those are the two expressions we have introduced. Magnetic field is generated using moving charges, or in this case, current carrying wires. And these are the two configurations we are talking about. So that's your straight line, and that's your R. And we started building more complicated circuit using these two elements. So let's do one example here, which involves slightly different configuration, and that's a triangle. In your homework, you do this for a square. The example is that what's the magnetic field due to a configuration involving a triangular current carrying wire. So there is a current I going through this wire, and since this is triangular, that's I. Keeps going in, and the understanding is that there is somewhere there is a source in there which we have not described that properly. This is an equilateral triangle of side length L. Equilateral triangle, that means this is 60 degrees. Each of those angles are identical in that. And what is the magnetic field at point P? If I give you what is the magnetic field at some arbitrary point, again that can be calculated because of the three straight wires, current carrying wires, each one of them has this magnetic field. You have to add them vectorially, and that makes you the total magnetic field. But the idea is that there is a lot of simplicity in at point P, because if you notice, the current contribution from this piece is this distance here, which is pretty much due to symmetry, exactly the same as those three wires. So I can say the total magnetic field will be equal to, let's see if it is in the same direction or not. If I hold the bottom wire, hold it using the right hand rule so that the thumb is pointing in the direction of current, and at point P, my fingers are coming out of the board. So at point P, due to the bottom wire. So let me call it 1, that's 2 and 3. Due to 1, it is coming out of the board. Due to 2, also it is coming out of the board. Due to 3, also it is coming out of the board. So it is just 3 times the same magnetic field due to 1 wire. So 3 times the magnetic field due to 1. Or due to 2, or due to 3. It is coming out, so let's say the hat resistance coming out. So that's equal to 3 times the hat. And this is a straight wire, so that's what this wire represents. That's your 1 wire, and it is given by mu naught over 4 pi times the current I in the wire that's given to us. So let's say I is, just so that you know what are the quantities given, 1 amps, and let's say L is about 5 centimeters. And the question is, what is the magnetic field at point P? So I is given to you, and what we need is this distance, if this observation point is here, how far is the observation point from the wire? And you have to go a perpendicular distance. When it's a line, but the closest distance from that line, that's what is important for an equilateral triangle. This can be found out. So let's say this is for line A for now. We will figure that out. What is that line A? So that's line A coming in. And it also matters what are these angles. So we have to talk about what is the sign of the angle that's formed here. Look at the one tip of the wire. What is the angle it makes with respect to the observation point? This is an equilateral triangle. This is the center of the triangle. That's 60 degrees. That will be 30 degrees. The center of the wire makes symmetric angle is exactly distributed in an equilateral triangle. The same thing in here. This angle gets divided by 2, so that's 30 degrees. So that's sine of 30 degrees plus sine of 30 degrees. Plus, because I'm measuring it. Oh, so that's not sine of 30 degrees, right? That's a mistake. Notice this angle meter is from the point of view of the observation point, not with respect to this. So it is this angle that is important. So let me change that. That's a mistake on my part. That was not intentional. So it's harder for you guys to do this. So that's, if this is 30 degrees, that's 60 degrees. So that's 30 degrees. And so since this is the right triangle, so that's 60 degrees. So this is not sine of 30 degrees. This is sine of 60 degrees. It's already clear that we can put in most of the numbers. I is known to be 1, except that line A, right? That's your line A. So let me draw this again. So that's your triangle clarity. That's 60 degrees. That's 30 degrees. That's 90, and that's your distance A that is coming in our expression. But what we do know is that this total length is L. So this is L over 2. So always we look for a right triangle. That's the basic idea. We usually know the geometry of a right triangle very much. And almost every triangle can be broken into right triangles. So look for right triangles. That's the main idea. Here it is A is not known, L by Q is known, L is 5 centimeters, and the angles are known. So since this is the angle that is important, so let's write it in terms of this. So if this is angle 60 degrees, that's your opposite over A, that gives you the tangent of 60. The tangent of 60 degrees is equal to L over 2 over A. that allows you to calculate A. A is equal to L over 2 divided by tangent of 60 degrees. Put in the numbers, the L is 5 centimeters, so it's 5 into 10 raised to minus 2 divided by 2 times tangent of 60. That's, I suppose, root 3. Or probably 1 over root. So 1.73, and which gives us that's 1.5 into 10 raised to minus 2. So I think I get this side so that I have space there. And this is in meters. We know everything else, so that's 3 times 3 hat times mu naught, remember is 4 pi into 10 raised to minus 7 divided by 4 pi. I is 1 amp. A is 1.5 into 10 raised to minus 2. And we have 2 times sine 60. Sine 60 plus sine 60. 4 pi cancels out, and we have 3 times 2, 6 divided by 1.5, that's 4. And 4 times sine 60. That's 3.5 into that's 10 raised to minus 5 remaining. The unit of magnetic field is Tesla, and it has a direction which is V hat. First one is the unit, second one is the direction. You get the idea of what's going on. You have a magnetic field due to one configuration. You can do this for many configurations. You just have to add vectors. Most of the time, since this is a three-dimensional geometry, we consider simple scenarios where the magnetic fields are aligned, but that need not be the case. We will do an example just now to show that that's not necessarily the case. In general, magnetic field here due to one wire could be in this way and spatially in different orientation. That's the basic idea. Any questions at this stage on the magnetic field due to wire? Let's do one situation where the magnetic field doesn't add up exactly like two aligned vectors, and that is again showing up in your homework. Let's have this is the reference axis, that's your x and y axis, and for convenience, let's have our observation point at the origin. That's your observation point P. Remember, P have been consistently using as the observation point. Whenever I write P, I mean that's where I'm interested in measuring the magnetic field. I need to have two currents. So let's say I have one of the currents somewhere here on the x-axis, but this time not in the plane of the board, but it is coming out of the plane of the board. This is like a current carrying wire like this, but it is coming out of the board. So that's the direction of the current carrying wire. It's coming out, and that's I1. And it is infinitely long. So this is infinitely long. It starts from minus infinity and plus infinity. Again, remember that might sound very unrealistic, but if your observation points like these distances are to two significant, which is 1 centimeter, and the length of the wire is 100 centimeters for all practical purposes. To the accuracy that we are dealing with, 100 centimeters is infinity to 2 significant compared to 1 centimeter. So it's not at all unrealistic. It's very much reasonable. All these results work very well. That's I1, and let's try another wire, that's I2. And let's say that's going into the board. two current carrying wires, one is coming out of the board, in one of the wires, the current is coming out of the board. In the second wire, the current is going into the board. I hope that's clear, how you imagine that. But now we want to calculate the magnetic field. This creates a magnetic field everywhere around it. How does it create? So hold the wire with the thumb pointing in the direction of the current. Current is coming out. So the curl of the fingers gives you the magnetic field. So that's your magnetic field everywhere around it. But I'm not interested in magnetic field anywhere. I'm interested in the magnetic field right at the center of the right at the origin. So that's your magnetic field lines, and they are counterclockwise because the curl of the fingers is here, but as it comes at this point, it is going down. And that is one particular circle, which I'm particularly interested in, and that's point A. And if I were to use my curl of the fingers right here, the tangent line is going in or going down. That's my magnetic field due to the first wire. Right? Notice how I argued that I used my right hand to realize that there are circles. At this point P, since it is right on the axis, it will be on a tangent to that particular circle, and it is pointing down because it is counterclockwise. It's pointing in the direction counterclockwise with respect to that circle. So at this point, magnetic field is going down. Do the same analysis with I2. I now have to, this is not coming out of the board, it is going into the board. Right? Cross means it is going into the board. It is going this way, and now again, this is clockwise this time. That's my circles. It is clockwise this way. That's clockwise, and I'm particularly interested in this circle, and again tangent to that circle, and it will be this way. And since this is slightly closer, it depends on angle or right. We don't know exactly which one is bigger and which one is smaller. Let's say that's B2. Realize that they are circular fields. This at this point it is tangent and it's going down, and the other one is going to the left. Those are your two vectors. We have to add the like vectors. So let's now put in some numbers just so that we can process them more easily. So let's say that I1 is 1 amp and I2 is 2 amps. That's your two currents. I also need to tell you what are the distances, how far this is decides how strong the magnetic field will be. This is inversely proportional to the distance, right? So if this is the Y, the observation point, how far it is this distance. So let's call this A, and that's B. A could be, so this seems to be slightly longer here. So let's say this is 3 centimeters, and that's 2 centimeters. So A is 3 centimeters, and B is 2 centimeters. And we would like to calculate the total magnetic field. So let's start with V1. V1 is equal to, it is direction we have to interpret from the diagram itself. It comes from the right hand rule. We have already used the right hand rule, and it is clear that it is pointing down. So that's minus j hat. So it is 0. 0 minus j hat. Minus because it's pointing down. And we have mu naught over 4 pi times the current I times the distance. Let me call that's A. So this is current I1. Distance A, because I1 is the distance A equal to 3 centimeters from the origin. And we need the sine theta 1 and sine theta 2. So an infinite wire, when it is an infinite wire, this point goes all the way out there, and this angle opens up all the way to pi by 2. And that means this is 1, sine of pi by 2 is 1. Since this is infinite wire, so that's sine of pi by 2 plus sine of pi by 2.
How does you follow it?
If you have an infinite wire, so that's your wire. Right?
What's the angle?
Yeah, so that's what I was just going to say. So this, if you have a wire, and let's say that's your observation point. Right, that's your point P. That's angle beta 1. The way I have it written there, that's your. And that's angle beta 2. And that's distance A. Now, if I like to take this point all the way to infinity, what happens to this angle? This point, as I move up, this opens up more and more. And all the way that goes to infinity, this is pretty much trying to catch up there, and that's 90 degrees. So that's that 90 degrees, sine of 90 degrees. And the same thing here, if I were to go very much to the bottom, this opens up completely, that's the maximum it can open up, and that will be 90 degree again. So that's sine of 90 plus sine of 90. Often, you just remember that if it's an infinite wire, it is 2. One from sine of 90, one from another sine of 90, it is 2 times I over A. So instead of doing this all the time, you just come across infinite wires so often that you just say it is 2I over the distance between them. That's very common, that's perfectly fine. If you immediately write this is 2 times I over A, that's okay. Like no one will be able to question it. Most probably no one will be able to question it. It depends on who is grading it, but in this course, it is okay to say that infinite wire is immediately 2 times I over A. Any questions on that? And how the angle is coming up? Did I clarify that? Okay, thanks. So that's 2 times this. So let's put this numbers also right away there. So let me do that number here. So that mu naught over 4 pi. I'll do that here and put the number here again. So it is 4 pi into 10 raised to minus 7. The negative sign is there in front. So that's 4 pi times current. I said it's 1 amp. A was 3 centimeters. So it's 3 into 10 raised to minus 2. And we have 1 plus 1, that's 2, right? So 4 pi cancels out. 2 divided by 3, so that's 0.67. 0.67 into 10 raised to minus 5. Remember, 10 raised to minus 4 Tesla is what you create due to the magnetic field of Earth. So it is weaker than that, but this is 1 wire. I can just make it 100 wires, and suddenly I have a magnetic field larger, 10 times larger than the magnetic field due to Earth. So it is very easy to scale this. They linearly add up. So if you do know for 1, you just immediately know that for 100 times and you make it better. So let's just put this number in there. So B1 is 0 minus j hat. And as a number, we have 0.67 into 10 raised to minus 5. I don't write the units just for avoiding the clutter. So that's what it is. And that's an SI unit. This is Tesla. You have to do the same thing for magnetic field due to 2. The second current carrying wire. This is in the minus I direction, right? So we argued already that this is your right hand rule to get the direction to be in the minus I hat direction, and there is no direction or no magnitude in the j hat direction. So that's 0 times that's that I hat. So that's what that 0 was sitting. So it's minus I hat, and we do the same thing for this wire, except that now the magnitude and the distances are different. So the magnitude of the current, so let's begin with mu naught over 4 pi times I2 over the distance now is b times, again it's infinite, So it is sine of pi by 2 plus sine of pi by 2 or 2 and plus 0 j. Put this again, it is pretty much the same except I2 now is double, so that's 2. So I have to multiply this by a factor of 2, and B here is 2, so it is divide by 3 and multiply by 2, right? In the denominator, I divide by 3 and multiply by 2, so it's 3 times. So I take this answer, I multiply by 3, and I get the same thing. Or get an answer. So it's 0.67 into 3, so it's so 20 by 3, so it's 22.0. So it's 2.0 into 10 raised to minus 5 plus 0. I did not calculate this, I just used, if you plug in these numbers, you will get this numbers. But we are interested in the total magnetic field at the observation point, so the total will be linearly added, but this time adding like vectors. Remember, like forces, if you're adding vectors, the x components add separately and the y components add separately. So I hat times there is a factor of 2 into 10 raised to minus 5 Tesla, and in the j hat direction it is 0.67 into 10 raised to minus 5, and this whole thing is having a unit of Tesla. If we are interested in the magnitude and direction, go back to your vectors idea and let's do that for magnitude of the magnetic field. What will be the actual strength of the magnetic field? That will be equal to, so you often say this is just the total. Whenever there is no vector sign, that means it is the magnitude. That's equal to 10 raised to minus 5, 10 is coming out common. The negative signs do not contribute, so it's 2.0 squared plus 0.67 squared, and then you take a square root. But I have to keep that 10 raised to minus 5 separately. That's like a unit, and Tesla. So that comes out to be so that's 2.1. So that's 2.1 into 10 raised to minus 5 Tesla. That's your total magnetic field. You would also like to know what is the direction of this magnetic field. These are two vectors now. We can make this a rectangle and say what is the angle. Let's say it is the angle with respect to the x-axis. We could ask what is the direction of that magnetic field. So theta would be tan inverse of in that right triangle that I have shown. It is opposite over adjacent, opposite is a y coordinate. So y coordinate is 0.67. You can write 10 raised to minus 5, but that's out. It's common in both. Divide it out, and that's equal to that's 19 degrees. And just to remove the ambiguity, not depending on the diagram, it is counterclockwise. Clockwise with respect to negative I hat. Angles are always better with respect to a direction. It's the minus x hat, and that's your 90 degrees with respect to that. So once you have the magnetic field to individual sources, then we can add them. Just make sure that you add them like vectors. So now, in separate contexts, we have shown how magnetic fields are created. And earlier, we have talked about how if we have a magnetic field, it can exert a force on a charge. And there is a moving charge creates a magnetic field, or a current carrying wire creates a magnetic field. But a magnetic field also exerts a force on a current carrying wire. But of course, the one that is creating it cannot get a force from itself. So you cannot have a force or the magnetic field that is created by the current itself is not going to exert a force on itself. That becomes a challenge when you're really doing the consistency check for all the things, and those are called what is called the self energy of a wire. We are not discussing that here. We will be having two wires. One wire can have the current I, creates a magnetic field that exerts the force on the second wire. So let's make this more concrete. So force, or let's say magnetic force, between wires, or current carrying wires to be more precise. Think of, just to have an intuition feel for it, you have these power lines going above on the roadside, and there are two wires that are parallel to each other. Is there a force between these two wires just because they are carrying current on it? That's the question we are asking. Two current carrying wires, is there a force between them? Remember, if you have a positive, two positive charges, positive Q1 and positive Q2. We know that there is a repulsive force in this. How do we look at it? This creates an electric field. So that's your electric field that's created. Right? That's your electric field everywhere around. So that's your electric field E1. Once you have an electric field E1, there will be a force onto by 1, which is Q2 times the electric field. If you had two charges, one charge creates the electric field, and that electric field exerts a force on a second charge. You're doing the same thing, but now we're talking about moving charges. That is a current or a moving charge creates a magnetic field. So let's say that's your magnetic field. It's usually circular. So let me clarify that. It will be circular magnetic field. So that's your V1. And then another charge that is moving. So that's Q2 and V2. So this charge, because it is moving, experiences a magnetic force this time, and we would like to calculate that. But here, we don't want to talk in terms of two moving charges. That can be done. But here we will say there are two wires. That is a current carrying wire I1. And there is another current carrying wire I2. And both are infinitely long. And we would like to know what is the force between these two wires. Are they attractive? Do they tend to attract? Or do they tend to repel each other? So that's going to be the goal. Let's begin with current I1. This is an infinite wire. There is a magnetic field that goes into the base everywhere on the right side. That's shown like this. And everywhere on the left side, it comes out. And as I go further, it gets deeper. from the beaker. Yeah, a distance that is going farther, and on the same thing on the left. That's your magnetic field getting weaker as you go out. As you go farther from the wire. This current carrying wire is on the right side of the current carrying wire I1. So I'm interested in the magnetic field at this point here. That is going in. That's going in. This is the magnetic field created by current I1. It's called that B1. That's what we have been saying. So the magnetic field B1 is equal to, let's have a coordinate system. That's your X. That's your Y. And then the V will be coming out of the board. The magnetic field is going into the board. So that's minus Z hat. That came from the right hand rule. So this came from the right hand. And it's an infinite wire, so it is mu naught over 4 pi times I over how far this is. Let's say this is distance d. That's distance d. And it's an infinite wire, so it is 1 plus 1. That's a factor of 2, right? Sine of 90, sine of 90. That's how we get that 1 plus 1. And that's the magnetic field everywhere on this, along this wire. There's a magnetic field here. There's a magnetic field here, everywhere on this. That's what this process of written, and I've made this more explicit by showing that there is a magnetic field everywhere where the current carrying wire exists. That's your magnetic field. The force on the second wire due to the first wire. So the force is on the second wire, on the second wire by the first wire is F21. That's given by the current I in the wire. Remember, is QB cross B, but if we are writing in terms of the current, so it is IQ times the length of the wire, that's L2. There is a direction associated with that length. Length is typically, you don't associate a direction, but this direction comes from the direction of the current. Is the current going up or down? And then it's crossed with the magnetic field due to the first wire. So the first wire creates a magnetic field, and that magnetic field exerts a force, and that's given by this, like before. What we studied about a week or so earlier. So let's put this all together. Use your right hand rule. L2 is going up in here, so that's your X or Y hat direction. And B is going into the board, so my palm has to face into the board. And if I open my thumb, that is going to the left. So the direction of my force will be to the left, and that is minus X hat. That's minus, let me call it minus I of X hat. I've been using Z hat. Again, four fingers point in the direction of the current, and there is a flexibility there of how you orient your hand, and orient your hand so that the palm is facing the magnetic field. Magnetic field is going into the board, so that's the direction of the magnetic field. And you open your thumb, and it is to the left, so it's minus X hat. And there is an angle of 90 degrees between the magnetic field going in and going into the board. The current is in the plane of the board, so that's sine of 90. So it is IQ times L2, that's the length of the first vector, B1, that's the length of the second vector, and sine of 90 degrees. That's the angle between, L1 and B1. oh, sorry, L2, right? L2. And B1. B1 is going into the board, L1 is on the plane of the board, the angle is 90 degrees. Now we have all the quantities that we need, so let's put this in, so that's I2 times L2, D1, substitute that from here we have already taken care of this direction, don't overcount them. We used our right hand rule to get this, so we don't have to take care of the negative sign or this we have. This is not a vector, that's a magnitude of that. That's mu naught over 4 pi times I1. I could have written I1 here, it's not capital here, this is I1. But if I correct this, it was written as I earlier. Now I have written this as I1, so I made a fraction there. So that's I1 over D, and that is a factor of 2. That's your expression for force between two wires. So force between two wires, two parallel wires, let's say. These are infinite length wires, so it doesn't make much sense to have a length in here because that is going to be infinite. So you talk about whenever there are infinite quantities, you say it is force per unit length. This is an infinite wire, but on a finite piece of the wire that will have a finite force, you say force per unit length, let's say L2 is equal to, this is minus x hat times mu naught over 4 pi times I1, I2 times a distance d. Let me change this variable factor of 2, right? Then cancel that and write this as 2 pi. Notice that is a negative sign in there. You should compare this with the force between two charges. This will be 1 over 4 pi epsilon naught. And that is Q1, Q2 over R squared. That's the distance between the two charges. So the force between two wires, they are slightly different. One is that this is of a different power. This is 1 over R squared dependent, and that is 1 over length. There's a factor of 2 extra in there. But more importantly, there is a negative sign there. What that means is that two light currents, right? Two currents that are going up, they will be called light currents, like light charges. They actually attract. Here, two positive charges repel. So the conclusion is that two light wires, light currents, if you want, light currents attract, and unlike currents repel. That's a very important distinction between magnetic field and electric field. The sources of electric field, that are the charges, they like charges repel, and unlike charges attract. Magnetic field, light currents attract, and unlike current repel. So very distinct feature in that, and that has a basic anywhere we have electrostatics and magnetostatics coming in, that energy associated with that has the difference showing up. That's your magnetic force. And the last 20 minutes, 15 minutes, I want to do one more thing, and that is to realize how do we create a uniform magnetic field. A current carrying wire has a magnetic field that dies off inversely. Force 2 on 1. Oh, did I write it wrong? Oh, 2 or 1, yes. Thank you. This is like Michael, so correction. 2, 1, so. Correct. Earlier I wrote 1, 2, so now it's 2, 1. If it is the other way, it will be on that side, so direction of the force is of course reference dependent, but either way, you have two quantities when they're trying to come together, you say that's attractive. When you're going farther, it is repulsive, so this statement is correct, but this is F2, 1, which is negative, that means it is going towards the other one. Thank you. Any comments or questions? When we were doing electric field, there was a nice theorem that worked for electric field, and that was that if you calculate the flux of the electric field about any closed surface, it will always pick the charge that is in there. The inside, the source is all that matters. That is a very similar feature with the magnetic field. And remember again, electric field, you call it Gauss's law. And it's a very striking feature in the sense there is a charge Q which creates an electric field. But you don't have to actually, and you would say, how do I know how much charge there is? But the basic idea of Gauss's law is that don't even go close to the surface or go close to the charge, stay away from it and measure all the electric field at this point on the closed surface. That's like saying there is Earth down there, stay very far away at the place where International Space Station is, but map the gravitational field completely enclosing your Earth. And if you map that electric field and calculate E dotted with, take the projection of the electric field on the surface element, and you add them all up. If you add the electric field somewhere very far from the charge, you're not even going close. You would like to, intuitively, we will say that if you want to know how much is the charge, you would like to go close to that. But we are saying stay away from it, but measure completely. Like you have to completely enclose it. That's the idea of a flow, right? If you know how much water is going out of the house everywhere, you don't have to know where the source is. You know that there is so much of source inside the water. If the house is leaking, that much of water is coming out. So that's the idea. An electric field is a flow. If I calculate all this, this will give you exactly the charge Q in it, except for a constant. Right? So electric field is a flow. The moment you accept that, Gauss's law is an immediate implication of that. Same idea with magnetic field. That's also a flow, but this flow doesn't have any sources in the sense that there is no single north pole or a south pole. So it is more of a curve. It always goes in circles. It is like a swirl in a, if you were to have, yeah, toilet, right? Whenever in a sink, water is going down, they make this circular flow. That's the idea of a magnetic field. Magnetic field is always circular. So that's the feature you want to keep in mind. And the idea associated in the spirit of Gauss's law is what is called Ampere's law. Ampere is the same person whose name is coming in the unit of current. And Ampere's law states that, let's do this for a single current carrying wire. So I have a current carrying wire which is coming out of the board. That's your I. Current carrying wire coming out of the board. And its magnetic field everywhere will be circular. Right, that's my magnetic field coming out of the wolfram, and the field gives me the magnetic field. So it's getting weaker. That's my magnetic field in there, but I don't want to really calculate the magnetic field very close. Instead, I go very far away. This time we don't have a surface that we enclose the magnetic field or the wire with. Instead, enclose it with an abstract circular loop. So this is an Ampere loop. Let's call it an Amperian loop. This is an abstract loop. This loop is not part of the magnetic field, it's not part of the wire, it's just an abstract circle that you can think of. Then give it a direction. Let's say that's the direction, and that's dl. And that's an infinitely tiny element of that. Keep it circular, that is for the symmetry. And if you were to calculate the magnetic field, draw the projection of the magnetic field in the direction of the loop, everywhere on the loop. It's a closed loop. So that represents a closed loop, right? It's a closed loop. If you do that, remarkably, you always get, in this case, there is only one current I that is there. You will always get the number of wires that is inside the loop. In this case, that is just one. Right? That's mu naught times I. If by any chance, if I were to put in, so you would say that, okay, what if I put in another wire in there? So let's say this is I1, that's I2, and this is I3 going in a different direction. And it doesn't have to be all coming straight. That could be wire coming in a tilted form. It doesn't matter. That's your 3. That's your I4. And always this will capture only the inside. Maybe I could, for that matter, I could also say there is an I5. There is an I6. And so on. So it is only the current inside, and that gives you V naught times current I1. I1 is coming out, so that's plus. I2 is coming out, that's plus. And minus I3 minus I4. And that's it. You stop there because I5 and I6 are outside. It has nothing to do with the numerically going in. I7 could be in, and then I include any current that is inside contributes, outside doesn't contribute. So it's a very straightforward thing to do. You do not have to do any algebra or an integral to calculate that. It is always equal to I1 plus I2. And if it is in the opposite direction, it is minus I3 and minus I4. It's only the inside part that contribute. Using this, let's try to now do this for a relatively complicated geometry, which we may not have a strict idea of what exactly the magnetic field is. And let me demonstrate this for one particular field. This is also part of the homework. So if I cannot finish this, I'll go a bit quickly here, but you should be able to see this in the homework again. So this is called a solenoid. Solenoid is a helical wires. So this is a coil of wire. Coil of current carrying wire. So this will look like this. And it keeps going. And let me draw this slightly so that I don't have this clutter of this wire crossing line. So they are very closely wound so that each of the wires is almost right next to the other. And I throw the wire there. There is current going in this. That's the current I going in this. Everywhere on the right side it is going into the page. That's the right side going into the page. That's going in, and on this side it's coming out. These are currents that are coming out. And I keep doing this every time. That's my coil. And you would like to know what is the magnetic field inside and what is the magnetic field outside. Remarkably, the magnetic field, this is a solenoid, the result is very straightforward. Magnetic field, first of all, the direction, you will hold the wire, it is going into the field. Remember, each of this is a circular field, but hold one of them, hold it in this point, it is going into the hole, and my right hand fingers tells me that it is somewhere here. This direction. And since it is infinitely long, symmetry tells us that it cannot be directed this way or that way. It has to be in the axial direction. So this is in the Z hat direction, let's say, on top of the Z hat. And then the main non-trivial feature is that you would expect that magnetic field is stronger, closer to the wires versus when you are at the center of the cylinder. It is like saying if you are in the closed sphere, where is the magnetic or gravitational field larger? Is it at the center or is it farther? It's not very clear, but it is uniform. The non-trivial part is that it is uniform magnetic field everywhere inside, and it is mu naught times current I. It depends only on the current and n. A number n, which is a property of this coil. N is turns, number of turns. Because that decides how many wires are there in a small density per unit length. That's it. That's what it is, and that is a constant. Current is a constant unless you change it with time, and that's your magnetic field inside the coil. Constant, uniform magnetic field. What is it outside? We expect that this will go in there and it comes back in there, and you would expect this magnetic field to be this way. But by the time it has to come out, it has to go all the way out of the wire and then act like the north pole or the south pole. And by the time it comes back, it is all the way at infinity. In fact, it is zero everywhere outside. So there is no magnetic field outside in the coil of solid. How do we show this? You have to first show that there are three pieces you want to talk about. But let's say there is a loop. This is the Amperian loop. That's the Amperian loop. The magnetic field is along the loop. So B dotted with BL. So B dotted with BL has to be equal to mu naught times the amount of current inside this loop. How many currents are there? That depends on the length of this loop. If I is going through in each wire, it is current times number of turns times the length L. So it is I times how many turns, number of turns per unit length. So I multiply that by L. That's what it is on the right side. And on the left side, here the magnetic field is zero. Here they are perpendicular to each other. That's zero. Three of the sides gives you zero. On this side alone, you get the magnetic field inside the loop times the length L. That's equal to mu naught times I times N over L. L cancels out, and that's the magnetic field inside. So it comes out very straightforward way. using Ampere's law, but it's not very clear why is it zero outside. So those things you will see in the homework when you are explicitly show that it's zero outside and it is a constant inside. I'll stop here. Thank you.